Hello everyone, welcome to Neso Academy. We are learning theory of computation, and in the previous lecture, we have understood what is DFA minimization. And now in this lecture, that is partitioning algorithm for DFA minimization, we are going to start with the very first method of minimizing a deterministic finite automata, that is partitioning algorithm. So in this lecture, we will cover the topic partitioning algorithm. Let's get started. Partitioning algorithm is a DFA minimization technique which you already know, in which states are divided into groups or partitions based on their behavior. So in partitioning algorithm, the states of the original DFA are divided into multiple partitions based on their behavior. That means if the states are having the same kind of behavior, we will place them in one partition. But if they are having the different kind of behavior, we will separate them into different partition. For an example, we have a DFA with 6 states: Q1, Q2, Q3, Q4, Q5 and Q6. And in partitioning algorithm, based on the behavior of these states can be divided into multiple partitions. Like here you can see, the set of states has been divided into two partitions. Partition 1 containing the states Q1, Q5 and Q6, and partition 2 containing the states Q2, Q3 and Q4, which means the behavior of the states Q1, Q5 and Q6 is same, and the behavior of the states Q2, Q3 and Q4 is same. But the behavior of Q1, Q5 and Q6 is different from the behavior of Q2, Q3, Q4. That is why we have divided into different partitions. Equivalent states are placed in the same partition and distinguishable states are separated into different partitions. So Q1, Q5 and Q6 are placed under same partition. Similarly, Q2, Q3 and Q4 are placed under the same partition, which means Q1, Q5 and Q6 are equivalent states. And Q2, Q3 and Q4 are also equivalent to each other. But Q1, Q5 and Q6 are distinguishable from Q2, Q3 and Q4 because they are separated into different partitions. Let's see the next point. The partitions are repeatedly refined until no further separation is possible. So it is not necessary that after one splitting, the partitioning algorithm will stop. No. The partitions are repeatedly refined until no further separation is possible, which means if we again check into partition 1 and partition 2, it can be further divided based on the behavior of the states. For example, partition 1 is again divided into two partitions, partition 3 and partition 4. Partition 3 contains two states, Q1 and Q5, which means Q1 and Q5 are having the same kind of behavior and they are equivalent states, while Q6 is a distinguishable state from Q1 and Q5. That is why it has been placed under a different division. So, finally we can say states belonging to the same partition are merged together. Once we reach a point where there is no possibility of further separation, then we can say that states belonging to the same partition can be merged together. So, if there is no possibility after the partition 3 to get divided into further partition, Q1 and Q5 can be merged together to create a single state. And in this way, the number of states of the DFA can be reduced. So I hope a basic introduction of partitioning algorithm is clear to you. Now let's actually minimize a DFA using partitioning algorithm. So, given is a deterministic finite automata. Here is the transition diagram of DFA that is given to us, and our objective is to minimize the given DFA, that is, to reduce the number of states of this DFA. Let's see the procedure of partitioning algorithm. Step number 1. Remove all states that are unreachable from the initial state. So in the very first step, we need to remove all the states that we cannot reach from the initial state. In the step number 2, we need to split the states into two partitions, final states and non-final states. So in step number 2, we need to divide the states of the DFA into two partitions. One partition will be containing the final states and another partition will be containing all the non-final states of the DFA. In step number 3, for each partition, check each pair of states. If any pair of states is distinguishable, split that partition so that only equivalent states remain together in the same partition. What does that mean? For each partition, we need to check each pair of states. And if the pair of states are distinguishable, that means they are having the different kind of behavior. We need to split that partition again so that only equivalent states can remain together in the same partition. Our ultimate goal is that equivalent states remain under the same partition and distinguishable states can be separated out into different partitions. Next step. Step number 4. Repeat the partitioning process until no further splitting occurs. This I have just told you that we need to repeat the partitioning process until no further splitting is possible. Let's see the next step. Step number 5. Once the partitions become stable, that means when we reach a point where no further splitting possible, merge all the states of the partition together and it represents a single state of the minimized DFA. So when no further splitting is possible, then the states contained in one particular partition will be merged together to create a single state of the DFA. In this way, the number of states of the original DFA will be reduced and our DFA will be minimized. Let's see the last step. Step number 6. Construct the transition table and diagram of the minimized DFA. So once we get all the states of the minimized DFA, we will create the transition table and transition diagram of our minimized DFA. So these are the 6 steps of partitioning algorithm. Obviously, these steps will make much more sense when we apply these steps to minimize the given DFA. So let's get started. Let's start from the step number 1. Remove all the states that are unreachable from the initial state. So first we need to understand what is the meaning of unreachable state. If we can never reach a particular state starting from the initial state, then that state is called as an unreachable state. So we need to start from the initial state and we need to check all the states, whether we can reach them or not. If we cannot reach them, those states are called as unreachable states. And according to the step number 1, we need to remove the unreachable states from our given DFA. So let's check all the states from the state Q0. So we will start from the state Q0 and let's check the state Q1. Here you can see we can easily reach from Q0 to Q1 from this transition. That is why Q1 is not an unreachable state. Now let's check Q2. From Q0, we can easily reach Q2 using these two transitions. That is why Q2 is also not an unreachable state. Now let's check Q3. From Q0, we can easily reach Q3 using this transition. That is why Q3 is also a reachable state. Let's check Q4. From Q0, we can reach Q4 using these two transitions. Let's check Q5. From Q0, we can also reach Q5 using these 3 transitions. And that is why Q5 is also a reachable state. So we have found that there is no state in this DFA that is an unreachable state. So in our solution, we can write there is no unreachable state in the given DFA. Now let's proceed to the step number 2. Step number 2. Split the states into 2 partitions, final and non-final states. Which means these are all the states of the DFA, Q0, Q1, Q2, Q3, Q4 and Q5. According to this step, we need to split all the states of the DFA into 2 categories or 2 groups or 2 partitions. First partition will contain only the final states and the second partition will contain only the non-final states. In this diagram, you can see that Q1, Q2 and Q4 are the final states and Q0, Q3 and Q5 are the non-final states. You can see Q1, Q2 and Q4 are the final states because they have been represented using the double circles. And Q0, Q3 and Q5 are the non-final states. So we need to create two partitions. The first partition will contain the states Q1, Q2 and Q4, which are final states, and the second partition will contain the states Q0, Q3 and Q5 because these are non-final states. So the set containing these two partitions, the first partition of final states and the second partition of non-final states, that set is called as zero equivalent. So our zero equivalent, which is represented using the symbol pi naught, will be equal to the two sets or the two partitions. The first partition is only containing the final states and the second partition is only containing the non-final states. In this way, we have calculated our zero equivalent and we are done with the step number 2. Now let's proceed to the step number 3. Now before understanding this step, first we need to convert this transition diagram into the transition table. I have explained you earlier that for the complex topics like DFA minimization, conversion of an NFA into DFA, to understand the transition table is much more simpler as compared to the transition diagram. So, this is the transition table for the given transition diagram. I hope you can all make this transition table very easily using this transition diagram. So, this is our transition table and we have just calculated our zero equivalent, pi naught. So, now let's calculate our 1 equivalent. So the partition that we are considering is this partition and we are taking the pair of state as Q1, Q2. So the pair of state that we are taking is Q1 and Q2. Now we need to check whether Q1 and Q2 are distinguishable or equivalent states. Two states are said to be distinguishable if their next states lie in different partitions, and two states are said to be equivalent if their next states lie in the same partition. So let's check for the states Q1 and Q2. For the input symbol 0. Q1 gives Q2 and Q2 gives Q2. So basically Q1 and Q2 gives the states Q2 and Q2. Now Q2 and Q2 are belonging to the same partition. Now we will check for the input symbol 1. Q1 on 1 gives Q5 and Q2 on 1 gives Q5. So the next states are Q5 and Q5. Q5 and Q5 are again belonging to the same partition. So Q1 and Q2 are equivalent to each other. Q1 and Q2 are not distinguishable states. That is why in the 1 equivalent also, Q1 and Q2 will remain together in the same partition. Now let's write 1 equivalent. 1 equivalent is represented using pi 1 and pi 1, it will be the set in which Q1 and Q2 will remain together in the same partition. Now we need to check for our state Q4. Now Q4 is to be checked with Q1 as well as Q2. But we have just seen that Q1 and Q2 are equivalent to each other. So we can check Q4 with any of Q1 or Q2. Let's check Q4 with Q1. So this time we are taking the two states Q1 and Q4. Now Q1 on input symbol 0 gives Q2 and Q4 on 0 gives Q2. Q2 and Q2 belongs to the same set. Now let's check for the input symbol 1. Q1 gives Q5 and Q4 gives Q5. Q5 and Q5 also belongs to the same set. This means that Q4 is also equivalent to Q1. And since Q1 and Q2 are also equivalent to each other, that means Q1, Q2 and Q4, all three will be equivalent to each other. And Q4 will not be separated from Q1 and Q2. So in pi 1, that is our 1 equivalent, Q4 will remain in the same set. And in this way, we got our first partition of 1 equivalent. Now let's check the another partition of our pi naught. Q0, Q3 and Q5. The first set of states that we are considering is Q0, Q3. So let's consider the two states Q0 and Q3. Now Q0 on 0 gives Q3 and Q3 on 0 gives Q0. Q3 and Q0 belongs to the same set. Let's check for the input symbol 1. Q0 gives Q1 and Q3 gives Q4. Q1 and Q4 belongs to the same set, which means that Q0 and Q3 are also equivalent to each other. That is why in the one equivalent, we will not separate Q0 and Q3 and they will remain together in the same set. Now let's check for the state Q5. Since Q0 and Q3 are equivalent to each other, we can check Q5 with either of them. This time let's check Q5 with Q3. So the states we are considering this time are Q3 and Q5. So we are taking Q3 and Q5. On input symbol 0, Q3 gives Q0 and Q5 gives Q5. Now Q0 and Q5 are belonging to the same set. Let's check for the input symbol 1. Q3 gives Q4 and Q5 gives Q5. Now Q4 and Q5 are belonging to the different sets. That means Q5 is not equivalent to Q3. And that is why Q5 cannot remain in the same set with Q0 and Q3. This means the second partition of our one equivalent will be only Q0 and Q3, and Q5 will be in the third partition separately. And in this way, we are done with our step number 3. And after completing the step number 3, we have got our 0 equivalent and 1 equivalent. Now, let's proceed to the step number 4. Repeat the partitioning process until no further splitting occurs. That means now we need to calculate 2 equivalent, 3 equivalent, 4 equivalent, and so on until no further splitting occurs. So now let's start calculating our 2 equivalent. While calculating 1 equivalent, we have considered the partitions of 0 equivalent. While calculating the 2 equivalent, we will consider the partitions of 1 equivalent. So let's start with this partition and take our states Q1, Q2. Q1 and Q2 on input symbol 0 gives Q2 and Q2. Now Q2 and Q2 both belongs to the same partition. Let's check for the input symbol 1. Q1 and Q2 gives Q5 and Q5, again belonging to the same partition, which means Q1 and Q2 are equivalent to each other, and in the 2 equivalent also, they will remain together under the same partition. Now, since Q1 and Q2 are equivalent to each other, so we can check Q4 with either of them. This time, let's check Q4 with Q2. So we are considering Q2 and Q4. On 0, they are giving Q2 and Q2 belonging to the same set, and on input symbol 1, they are giving Q5 and Q5. Q5 and Q5 again belongs to the same set, which means Q4 is also equivalent to Q2 and Q1, and in the 2 equivalent, this partition will not be splitted and this partition will remain as it is. Now let's talk about this partition, Q0 and Q3. We are considering the states Q0 and Q3. Q0 and Q3. On 0, it is giving Q3 and Q0 belonging to the same partition, and on 1, it is giving Q1 and Q4. Q1 and Q4 also belonging to the same partition. That means Q0 and Q3, this partition will also not be splitted and will remain as it is in our 2 equivalent. Now let's talk about the third partition, which contains a single state Q5. Since this partition only contains a single state Q5, this cannot be checked with any other state. So this partition will also remain as it is in our 2 equivalent. So finally, we will get our 2 equivalent as pi 2 containing all 3 partitions that are exactly same as the 1 equivalent, which means no further splitting has occurred. This means we are done with our step number 4. Now let's proceed to step number 5. Once the partitions become stable. So as we can see, partitions are now stable. What we have got in 2 equivalent is same as what we have got in 1 equivalent, which means if we calculate 3 equivalent also, we will get the same result as the 2 equivalent. This means pi 2 is equal to pi 1. That is why partitions are stable now. Merge all the states of a partition together and it represents a single state of the minimized DFA. That means these 3 partitions, these 3 states will be combined together to form the one single state of the DFA. These 2 states will be combined together to form the second state of the DFA, and this will be the third state of our minimized DFA. Finally, we can say the states of minimized DFA are Q1, Q2, Q4 combined together as Q1, Q2, Q4, Q0, Q3 as combined together, and Q5 as the third state of our minimized DFA. Now let's proceed to step number 6, which is our last step. Construct the transition table and diagram of minimized DFA. So we have just seen that the states of minimized DFA are Q1, Q2, Q4, Q0, Q3, and Q5. These 3 are the states of minimized DFA. And this is the transition table of our original DFA. First, we need to check what are the initial and final states of minimized DFA. So, the initial state of original DFA is Q0. That is why the state which contains Q0 will be the initial state of minimized DFA. That is why Q0, Q3 will be the initial state. Now let's check the final state. In the original DFA, Q1, Q2 and Q4 are the 3 final states. So all the states of the minimized DFA that contains either Q1, Q2 or Q4 will be the final state of minimized DFA. Fortunately, we are getting Q1, Q2 and Q4 under the same state. That is why this will be the final state of our minimized DFA. So now we will construct the transition table of our minimized DFA. This is the basic structure of our transition table. There are only 3 rows because there are 3 states in the minimized DFA. And we can write it as this. Q0, Q3 is the initial state, Q1, Q2, Q4 is the final state, and Q5 is just an ordinary state of our minimized DFA. Now we need to fill these cells. Q0, Q3 on 0. Let's check. Q0, Q3 on 0 gives Q3, Q0. And we can see Q0, Q3 is the state of our minimized DFA. So here we will write Q0, Q3. Now Q0, Q3 on 1. Q0, Q3 on 1. We are getting Q1 and Q4. Now Q1, Q4 is not the state of minimized DFA, but the state containing Q1 and Q4 is this one. So here we will write Q1, Q2, Q4. Now let's check Q1, Q2, Q4 on 0. Q1, Q2, Q4 on 0 gives Q2, Q2, Q2. But Q2 is not a state of our minimized DFA. So the state containing Q2 is this one. So here we will write Q1, Q2, Q4. Now Q1, Q2, Q4 on 1. Q1, Q2, Q4 on 1 gives Q5, Q5 and Q5. Q5 is the state of our minimized DFA. So here we will write Q5. Now let's check for the state Q5. Q5 on 0 gives Q5 and Q5 on 1 also gives Q5. Q5 is the state of our minimized DFA. So here we will write Q5 and Q5. This is the transition table of our minimized DFA. And once we got the transition table of our minimized DFA, it is very easy to convert it into the transition diagram. So this is the transition diagram of our minimized DFA with respect to this transition table. Q0, Q3 on 0 gives Q0, Q3. Q0, Q3 on 0 gives Q0, Q3. Q0, Q3 on 1 gives Q1, Q2, Q4. Q1, Q2, Q4 on 0 gives the state itself. Q1, Q2, Q4 on 1 gives Q5. Q5 on both 0 and 1 gives the state Q5 itself. So this is the transition diagram of our minimized DFA. As I have already explained you earlier, that it is inconvenient to write such big names under one circle as a single state. So we can anytime replace these three states with our English uppercase alphabets like A, B, C, so that our DFA can look much simpler. So in this way, we have minimized our original DFA into this DFA. So if you remember, our original DFA has 6 states, but our minimized version of the same DFA contains only 3 states. So this is the partitioning algorithm for DFA minimization. And we are done with our topic, partitioning algorithm. In the next lecture, we will solve one more problem on partitioning algorithm. So this was all from my side for this lecture. Thank you, and I'll see you in the next lecture.